Welcome, everyone. Thank you for inviting me to deliver this talk at IEDM. I'm going to cover some recent advances in processing in DRAM. Before that, I'm going to motivate memory-centric computing and give some overview of it as well. Computing today is bottlenecked by data. All important workloads are data intensive. They require rapid and efficient processing of large amounts of data. And on top of this, data is increasing. We can generate more data than we can process, and we need to perform more sophisticated analysis on more data. And this is not going to change anytime soon. This is clear in machine learning models. These have been growing exponentially in recent years. And you can see that both compute requirements and memory requirements have increased by orders of magnitude in just a few years. And this is true for genomics also. There are technologies where we can generate huge amounts of sequencing data today, and this is being exploited, except we don't know how to analyze this data extremely efficiently today. The problem today is we have a huge data access bottleneck. It's really the major performance energy bottleneck in the design of today's computers. And our current computing design principles cause great energy waste because we're moving data from the sensors to the storage to the memory hierarchy, main memory to the caches to the registers, and then back and forth and back and forth and back and forth. And we try to overcome the performance loss effects of it by making our systems more complicated, by enabling complicated memory systems, out-of-order execution engines, accelerators, etc. But this also adds a lot more complexity and a lot more energy waste to our systems. And the main problem is our processing systems are processor-centric. All data has to go to a processing logic in the processor at great system cost. And in our current systems, most of the system, including the processor chip, is actually dedicated to storing and moving data. If you look at a chip, more than 95% of a single node is full of structures that store and move data. And unfortunately, we're still bottlenecked by memory. There's a lot of data that shows this. I'm going to very quickly mention this paper from Google that was written about a decade ago that shows that according to them, all of their data center workloads, most of the time on a state-of-the-art processor, spend most of the time waiting for data to come back from memory. The processor does what it's supposed to do only 10 to 20% of the time. Now, that was performance, and there's a lot of work that shows that performance is heavily impacted, negatively impacted by moving data, but energy is even worse. According to a lot of results, memory access consumes about 2 to 3 orders of magnitude the energy of a complex addition. And moving data to actually do a energy simple operation in the processor is very costly because it's very hard to amortize the energy cost of moving data back and forth from memory. If you would like to amortize the energy cost, you need to have a lot of locality. In many of today's workloads, we don't have that much locality. And people are trying to actually make the arithmetic operations much more simpler today. And unfortunately, as you make the arithmetic operations simpler, the relative cost of memory access increases greatly. So this shows a disparity between a memory access and a 32-bit integer addition, which is about 6400x. And we're not even talking about storage yet. We did a lot of studies together with Google and other collaborators to show the impact of data movement on energy on modern devices. In mobile devices, in general use cases, we found that more than 60% of the total system energy is spent on data movement. This is shown in this paper. I'm not going to go into a lot of details of this, but this is on average use cases. There are many use cases where this number is much, much higher. We've also repeated the study on machine learning accelerators that are used in the edge using machine learning models that are used at Google. And we found out that more than 90% of the total system energy is spent on memory in some of the large machine learning models. So this number becomes much worse in some applications. And this is a specialized accelerator where data movement is actually optimized as much as possible. This shows some example results. Here we show that on large models like LSTMs and transducers, the machine learning accelerator is spending most of its energy on DRAM access and off-chip interconnects. So the fundamental problem we're trying to solve is that the processing of data is performed far away from the data. We really want to enable computation with minimal data movement. We want to enable computation where it makes sense, where data resides, opposed to just moving the data to processor. And we would like to make computing architectures more data-centric. This clearly requires a paradigm shift. In the end, we would like to enable computation anywhere, everywhere, where data may be present or data may be produced. And we would like to schedule that computation accordingly so that we get the best out of this computation capability. And there are many places where we can do this computation, clearly sensors, storage, DRAM, processing chip, and we would like to enable it everywhere. And we would like to think of memory as an accelerator in the rest of this talk. We'd like to treat memory as a conventional accelerator. We're building a lot of accelerators to improve energy efficiency and performance of our systems. And we would like to have accelerators on the memory side as well that are more memory-centric. And this will ease programming, although we will see that programming will be an issue throughout. So our goal is to really enable processing inside memory and storage devices and other places. If you just look at memory, which we're going to focus on from now on, we would like to enable querying memory with questions like, can I execute this function on you, memory? And the memory could respond with results. There are many questions over here that span across the stack: algorithm level, programming level, system software level, hardware software interfaces, microarchitecture, logic, devices. And clearly there's a rich research across the stack. I'm not going to cover all of the research problems. Our paper touches on some of them, but I will cover a specific approach to processing in memory. But before I said that, I should say that this is not a new idea. Clearly, people have thought of this in 1950s, 1960s. First papers appear in 1960s. I'd like to acknowledge them over here. What's different today is we have nowhere to escape. Essentially, from an application and system perspective, we're really bottlenecked by data, and we can improve all metrics like performance, energy, and sustainability by minimizing data movement. From the technology perspective, we're really bottlenecked by scaling issues that really demand more intelligence, like computation in memory. RowHammer and RowPress are examples of this that we have worked on, and these are actually changing the DRAM chips today such that computation is incorporated, controllers are incorporated into the DRAM chips to solve some of these scaling issues. And there are also emerging technologies that can enable new functions in memory, like 3D stacking. So today, I think we're squeezed kind of in the middle, and we really need to move to this new paradigm shift. That said, I think we should think about processing in memory fundamentally also in a different way. There are two approaches to processing in memory. One is processing near memory. The other is processing using memory. Very quickly, processing near memory doesn't change the logic today as much. You have logic and memory, and you bring the logic closer and closer and closer and closer to memory. It could be on the same die as memory. It could be on the logic layer of 3D stacked memory. It could be in different places, essentially. But logic and memory are separate. Processing using memory is fundamentally different. It basically, you kind of forget about the logic. You use the operational principles of memory cells and circuitry to perform computation. We're going to focus more on processing using memory. That said, processing near memory is easier to implement. You can put more sophisticated functions because you use conventional logic. So many of today's incarnations of processing in memory landscape chips, as you can see over here in this picture, and many other experimental chips and startups, are based on processing near memory. I'm not going to talk about processing near memory as much, except I will say that there's a lot of interesting developments in this area. Our paper covers some of them. I will mention some other paper over here. And interconnect technologies like Compute Express Link makes it easier to enable. There are also three-dimensional technologies that enable this sort of processing near memory much more nicely by implementing things in the logic layer, for example. And we have done work in this area. I'm flashing some papers over here. And there's more work in this area in graph pattern mining, graph analytics, machine learning, mobile workloads, and also genomics that I mentioned. And also this processing near memory can be extended to other devices like storage, as we have done in recent work, which I'm not going to talk about. There are many more examples of this, as well as processing using memory in our long archive paper that we're going to update very soon. But with that, I'm going to jump now into processing using memory, and a particular type of processing using memory, processing using DRAM. We're going to focus on DRAM because DRAM is the major main memory technology. It has large capacity, low access latency. It can support many workloads. I'm going to demonstrate that we can natively support bulk bitwise operations in DRAM, and or not majority nor NAND, bulk bitwise copying and initialization, true random number generation, and more complex computation as well. We can do most of this at low cost. In fact, basically, we're going to use the analog computation capability of DRAM, but we're not going to do completely analog computation because there are digital to analog converters, analog to digital converters in DRAM that enable nice, reliable operation. We're going to activate multiple rows to perform computation, can either do it sequentially or consecutively. And we were going to show that these operations are possible even in commodity off-the-shelf DRAM chips that are unmodified if we just modify the memory controller and violate the timing parameters, which is really fascinating. We're going to see significant performance energy improvements as we go along. We're going to start simple first. We're going to talk about data copy and initialization. This is an area that data copy and initialization happens in many workloads today. In fact, Google, in the paper that I mentioned earlier, showed that 5% of their execution cycles in the data center is spent on two function calls, memmove and memcopy, which is fascinating. So we do like to do this in memory. Essentially, if you today, you have to go through the processor to copy data or initialize data. Imagine initializing tens of terabytes of data. This is really a huge waste of energy and performance. Why don't we just do initialization of data inside the memory? This is clearly low latency, low bandwidth, no cache pollution, no unwanted data movement. And I'm going to show you a mechanism that takes 1,000 nanoseconds, 4 kilobyte page copy to 90 nanoseconds unoptimized, and 3.6 microjoules to 0.04 microjoules. And the key idea is very simple. We're going to look at an internal of a DRAM subarray. If source and destination rows, pages, are in the same DRAM subarray, you first activate the source row, which brings the data into the DRAM sense amplifiers. And then in the next step, you can quickly activate the destination row, which brings the data from the sense amplifiers to the destination row, because the data is very strong in the sense amplifiers. Basically, by using sense amplifiers as a buffer internally, we can move the data quickly between a source row and a destination row. We show that this can be done very quickly at negligible hardware cost. It can improve the copy performance by more than an order of magnitude and copy energy by between 1 to 2 orders of magnitude, which is, I think, quite good. And we've shown application level results that show this benefit. I'm not going to go through this in detail. There are a lot of improvements on this. You can do fine granularity copies between different banks, etc. You can actually change the DRAM microarchitecture a little bit so that you can make the copying between the subarrays much better and efficient than possible. But I will now move on to computation. If you want to do computation in DRAM, one way of doing it is really enabling triple row activation. I'm showing you 3 rows over here, A, B, C, 1 cell in each row, and then a bit line, and then the sense amplifier. You can see 3 word lines and 3 access transistors over here. Now, if you concurrently activate these 3 rows, capacitors in those 3 rows share the charge with the bit line. If at least 2 cells are charged, you get the charge state at the end. If at least 2 cells are discharged, you get the discharge state at the end. Now, this is a bitwise majority function that's operating based on charge sharing principles of the DRAM circuitry, and eventually the analog charge sharing is amplified so that you get a digital value in the sense amplifier. Now, bitwise majority is beautiful. You can actually rewrite it this way. If you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. Now, if you have bitwise majority and then OR functions, you also have the bitwise inversion function, because the other end of the sense amplifier, when you activate one row, actually is the complement of the value of the row. I've shown you 1 bit over here, but a row can be 8 kilobytes, for example. You do this on 8 kilobytes. And if DRAM has thousands of subarrays, you could do this on tens of millions of bits concurrently. So the computation capability is huge, and there's a lot of parallel computation capability. We showed, when we actually realized this, in circuit level, we showed using simulation that many workloads can benefit. And this is one example. In databases, for example, you can get 4 to 12x performance improvements with commensurate energy benefits. I will not go through these old results, but you can make this very programmable. We actually worked on making this programmable. You can implement any operation if someone expresses that operation using AND or NOT logic over here. And any operation can be expressed this way. You can do convolution, matrix multiplication, division, and any kind of function, essentially, simple or complex. We generate a majority inverter graph based on this. Using these design automation tools, we optimize this majority inverter graph and convert the operation into a sequence of DRAM commands that consists of triple row activation, row clone, and some registry allocation, etc. And we store this operation in memory, this microprogram in memory corresponding to each operation. When this operation instruction is called by an application, this instruction is shipped to the memory controller, and the memory controller executes the microprogram associated with the operation. This way, using these instructions that trigger microprograms in the memory controller, you can actually execute any operation. And we see significantly more performance benefits compared to CPUs and GPUs on real-world applications. Now, more recently, we made this substrate more flexible. One of the issues is if you actually do these operations, you're limited to row granularity. And a row is 8 kilobytes. Unfortunately, 8 kilobyte granularity type of parallelism may not always be desirable or possible in applications. So we actually enable fine-grained DRAM by segmenting the global word line so that we can actually do the operations in smaller chunks of the DRAM, in DRAM mats, essentially. We can do this in individual DRAM mats. And this is an area where a lot of work has been done. People have shown that global word line can be segmented so that you can access individual DRAM mats. We're exploiting that. We've actually developed a way of doing this. I'm not going to go into this detail, but the paper explains it a little bit. Now, if you have fine-grained DRAM, and you do processing using DRAM for this, you can improve SIMD utilization. You can improve for a single processing using DRAM operation. You can only access the DRAM mets with the target data. And for other parts of the DRAM, you can actually perform other operations in other parts of in other mets. This enables a multiple instruction, multiple data execution model, which improves parallelism and performance. We also add low-cost interconnects for vector reduction. This is processing near memory actually inside the DRAM chip. I'm not going to talk about that in detail, but the paper again discusses this. We also can ease programmability if we have this mat level granularity, because now parallelism in a DRAM mat is on par with the vector ISA's single instruction multiple data width, for example, an AVX instructions width. We add compiler support to transparently extract parallelism from an application and schedule these instructions while maximizing utilization. So we actually changed the LLVM compiler, add 3 new passes to target processing using DRAM execution that I'm not going to go into. These slides talk a little bit about that, but essentially we need to take into account the mapping and scheduling across different DRAM mets. And finally, we generate a binary transparently to the programmer that enables this. And the results are significant. I will not go into a lot of detail over here. The paper has a lot more detail, but essentially we can improve the performance per watt compared to a CPU by more than 500x and compared to a GPU by more than 13,000x if you do this. Of course, in applications where this works. In application where this doesn't work, then we have an adoption issue, and we're going to talk about that later. Now, in the rest of the time, I will very quickly talk about the fact that what we're talking about is modifying DRAM. Yes, that's true, but existing DRAM chips already have a lot of this capability. We just need to make it more reliable, and we just need to think about DRAM such that we can enable these operations in a reliable and supported way. I'm going to show you some results that we have done. Essentially, by violating timing parameters in DRAM, you can do row clone operations. You can generate true random numbers. We actually designed an FPGA prototype that can enable this end-to-end in end-to-end applications. In this prototype, we have a RISC-V processor in the FPGA, and when the application executes a page copy operation or a true random number generation call, these calls are sent to the memory controller. Memory controller violates the timing parameters, does a back-to-back activate, for example, to do page copy. There's, of course, mapping mechanisms in the system that I'm not going to talk about over here. You can read the paper for more detail. And the memory controller actually enables page copy inside the DRAM without without bringing any data to the processor. And we see significant benefits out of this with a wimpy RISC-V processor. But this is actually very interesting to do. We'd be happy to support people's exploration in this area. So we also more recently showed that DRAM chips are more capable than just doing row clone and true random number generation. They can actually do these Boolean functions. In fact, they could be functionally complete. I'm going to show you 3 major results. We showed in real DRAM chips, unmodified, by just modifying the memory controller, but not the DRAM chips or the interface, we can copy 1 row into up to 31 other rows in the same subarray with almost perfect success rate. We can perform the NOT operation with up to 32 output operands, and we can perform up to 16 input AND, NAND, OR, and NOR operations. This is fascinating because now we have functionally complete DRAM by violating the timing parameters. The key idea is to violate the timing parameters such that you can do consecutive or parallel, concurrent multi-row activation. So this is an example over here. If you simultaneously activate many rows, you can copy 1 row's content to multiple destination rows, and we show how you can simultaneously activate many rows in a DRAM chip. I will show that in real results. NOT operation I already mentioned. If you have the source value in the top subarray and the destination value you wanted in the bottom subarray, you can actually violate the timing parameters by consecutively activating rows, and you can connect the rows and neighboring subarrays together. If you actually do an activate, the data gets into the destination, and if you actually do the second activate the destination concurrently, the data gets latched into the destination through the sense amplifier. Now, you can actually generalize this by doing simultaneous row activation in neighboring subarrays. You have the top subarray on the top over here. You have the bottom subarray on the bottom. The top subarray houses 2 cells, A and B. The bottom subarray houses 2 cells, X and Y. Now, if you concurrently activate all of these cells, meaning all these 4 rows, the function that is computed by the sense amplifier is really an average voltage of the AB cells on the top and the average voltage on the XY cells on the bottom. So it's really a comparison function that's performed. Now, if you manipulate the reference voltages accordingly at the top, you can do the computation on the bottom cells. For example, here we show that if the top cells are set to VDD and VDD over 2, and we have ways of doing that in DRAM, the bottom cells, the computation function that you would get on the bottom cells when you activate all 4 of these cells is an AND function, and you would get the NAND function of X and Y on the top cells. Now, this is fascinating. We showed that this can be done reliably. Now, let's take a look at some of the results. We could actually do AND, NAND, OR, and NOR operations, and the paper has a lot more detail on this. We have built a DRAM testing infrastructure that we have been using for more than a decade, which we've done on many studies on. We call it DRAM Bender right now. We actually support it. This is completely open source. It can work on DDR4 as well as HBM DRAM chips. We can do fine-grained control over DRAM timing commands, timings, temperature, data patterns, a lot of things in DRAM. We have tested a large number of DRAM chips from 2 to 3 major DRAM manufacturers in different works. And we've shown that multi-row copy can be done quite robustly with an average success rate of greater than 99.98% in these DRAM chips. That's fascinating. We could do it almost perfectly. And the data pattern doesn't affect it significantly, although there's an effect. We also look at temperature effects in the paper. And for AND, NAND, OR, and NOR operations, commercial off-the-shelf DRAM chips can perform these operations by doing multiple row activation by violating the timing parameters again. And the success rate is actually could be quite high, more than 94%. Of course, it depends on the number of input operands, etc. But it's fascinating that the chips are able to support this operation with very high success rates, even though chips are not designed for this purpose. This shows the fundamental computation capability that's present in the chips. Data pattern, again, affects things. And in the paper, we have a lot more results on temperature, spatial variation, temporal variation, etc. There's more on functionally complete DRAM in this work, and there's more on multi-row copy in this work that I'm not going to talk about. We can actually do a lot more using commodity memories. I don't have time to talk about these, but we can generate true random numbers in different ways. Multiple row activation and row activation is one way of generating random numbers. If you initialize cell values such that they're kind of balanced, you can, and you do n row activation, you can sample random values in sense amplifiers, and these could be quite high throughput and low energy. And we've shown that in the IEDM paper that by simultaneously activating 8 rows, you can get the highest TRNG throughput. You can also do system-level designs for true random number generation, as I talked about earlier. You can use DRAM for physical unclonable functions, and you can implement more sophisticated operations using lookup table-based execution that I'm not going to talk about. We can do almost all of these operations in Flash. I don't have time to talk about this, but this is a paper where we showed in using real DRAM chips, you can do processing using Flash in a similar fashion. So I've covered processing near memory. I didn't talk about that as much. I've covered processing using memory, specifically processing using DRAM. There's a lot more that we cover in our modern primer paper. I would encourage you to check that out. I will very briefly talk about adoption issues. So clearly, there's a lot of hardware that's coming out. There's a lot of hardware that's really possible in processing near memory as well as using memory. Unfortunately, the most important things are really the adoption issues. And these adoption issues are not just the design of hardware, which is part of it, design mindset and testing of hardware, but most of it is really related to the system, like applications, software, ease of programming. How do you enable system and security support? How do you enable runtime and compilation systems? And how do you enable infrastructures so that we can assess the benefits and feasibility? And how do you enable robust operation across the board? I believe all of these can be solved with a change of mindset. And part of the reason why we're doing these studies with real chips is to demonstrate that existing DRAM chips actually have the fundamental capability if we actually think of them in slightly different ways, such that they're not storage devices, but they're also computation plus storage devices. I believe we will need to revisit the entire stack to enable this sort of memory-centric computing processing using different technologies. Now, let me conclude. We would like to have fundamentally energy-efficient architectures that requires us to think in a more data-centric manner. We would like to have fundamentally high-performance architectures that also requires us to think in a fundamentally data-centric manner. We would like to have computing architectures with minimal data one. That means that we will need to have processing in memory, both processing near memory as well as using memory. So our goal is to enable that. And we highlighted major recent advances in processing in DRAM specifically. I've shown that this can lead to orders of magnitude, energy, performance, and energy efficiency improvements. And we've also shown that, fascinatingly, unmodified DRAM chips are already capable of almost all of these forms of computation without any modification. You can actually just modify the memory controller and violate the timing parameters. We believe memory should be designed as a combined computation and storage substrate and not as an inactive storage substrate. This means that our design mindset and flow should change from the very beginning, from the very fundamentals. I believe the future of truly memory-centric computing is bright, and I believe we've shown some results to demonstrate that. But we've also discussed in the paper that we need to do more research and design across the computing stack for adoption. And most importantly, perhaps we need to change our mindset and infrastructure and shift it to a more memory-centric place. Thank you very much. I'd be happy to take any questions.